So now let's talk about energy. The concept of energy is one of the most important topics in science and particularly in physics or engineering. The energy approach to describing motion is particularly useful when the forces are not constant. A little side note here, remember in this case our standard constant acceleration kinematics that we've been talking about, all these equations will not apply. So in order to talk about energies, first we have to talk about the forces that are involved. So for example, if you wanted to lift one thing from one place to another, there are a couple of ways you do that. For example, if let's say I wanted to lift, bricks from the first floor to the 20th floor during construction, there are two things I could do. I could lift them straight up, which means we will require a larger force, but it will require a shorter distance, and the time will also be shorter because the distance is shorter. However, if you wanted to apply less force, then you have to increase the distance and you have to build a ramp of some kind, put the thing that you want to move up through that ramp. The individual force that needs to move that thing will be smaller, but you will have to cover a large distance. So now it depends on the situation. If you have a longer distance, you can apply a smaller force, but if you have a shorter distance that you're worried about, you need a larger force. Types of forces. There are two basic types of forces, or in other words, we can say all forces can be defined in terms of two basic criteria. One is conservative and the other one is non-conservative. The conservative forces include gravity, spring force, and all microscopic forces like electromagnetic, weak, strong nuclear force. All those forces are conservative forces. Non-conservative forces are forces, say, friction or tension. These forces are macroscopic forces, and they are macroscopic, they are non-conservative due to the random kinetic energy of individual molecules. So now let's talk about these forces a little bit more. So in physics, a force is conservative if the work it does on an object moving between 2 points is independent of the path taken and only depends on the end points from where it started to where it ended. A force is conservative if the work done by the force on a closed path is zero. So work only depends on the initial position Ri and the final position Rf. If an object moves in a closed path, then the total work by the force is zero. So let's consider the first case. Let's say I want to move something from point A to point B, or from point B to point A. There are multiple paths I could take. For example, I could go this way to move from point A to point B, and that work will be work 1. Or, on the other hand, then I move it back from point B back to point A. They are completely different points, but if the work required to move them from one place to another there's no loss of energy, then that basically means this is a conservative force. The other one was, let's say I wanted to move this box from point A to B to C to D to point A, and there's no work done in moving it all the way over. This is called a conservative force. A non-conservative force is the work done by a force, say friction, on a closed path is not zero. In this case, the work does depend on the path it takes. So for non-conservative forces, there is a energy that is called the dissipative energy that gets lost while moving it from one path to another. So in regular life, we've noticed that people tend to use not any path that they take, but the shortest possible path to move it. And the reason is because planet Earth, we have dissipative forces like friction and thermal energy and heat and all of those stuff, and we want to minimize them. So non-conservative forces are those forces in which the work done by a force on a closed path is not zero, and the work done does depend on the path that the object took. So in conclusion, we can say a force is conservative if the work it does on a particle that moves through the round trip is zero. Otherwise, the force is non-conservative. A force is conservative if the work done by it on a particle that moves between 2 points is the same for all points paths connecting this. Otherwise, the force is non-conservative. So now let's talk about conservation of energy. Energy cannot be created nor destroyed. It can, however, be converted from one form to another, and the energy of an isolated system of objects remains constant. If you were to put a watch on this table and walk away at night, that watch should be there in the morning, unless some external force acts on it. Mechanical energy is the sum of potential and kinetic energies of an object. The total mechanical energy of an isolated system of objects remains constant if and if only the objects interact only through conservative forces. And the third thing to recognize in this one is the total work equals the change in kinetic energies. If all forces are conservative, then change in energy, the work done is equals to minus delta U, which is the symbol for potential energy. So the most important equation for you to remember in this slide is this one. Change in potential energy plus change in kinetic energy equals the change in the total mechanical energy, which is equals to 0. The law of conservation of energy states that the total energy of the universe is unchanged by any physical process. Energies can be converted from one form to another form, but we cannot create energies. There are three kinds of energies, basically three kinds of energies: kinetic, potential, and rest. Energy may be converted from one form to another, or they could be transferred between bodies, but the total energy of the universe will remain unchanged. Some common forms of energy that we deal with every day are translational kinetic energy, gravitational energy, rotational kinetic energy, vibrational, sound, seismic, internal, electromagnetic, chemical, and nuclear, and so on and so forth. All of those energies are created by some form or another. By, say, a battery converts chemical energy, and it does work, so it converts the translational kinetic energy of something, and so forth, so on and so forth. But these energies cannot be created out of thin air. So now let's talk about the basic types of energies. So the basic types of energies are kinetic and potential. Kinetic energy is, as the word implies, due to the motion of an object. So when an object is in motion, its kinetic energy is half its mass times square of its velocity. The potential energy is, as the name implies, the potential of an object to do work. It is the rest mass energy, or it is the energy that something contains by the virtue of its position in terms of gravitational potential energy, or in terms of chemical, if it's the battery that's sitting there that can do work. For gravitational potential energy, the formula for potential energy is mg delta h, where m is the mass, g is the acceleration due to gravity, and delta h is the height. Kinetic energy, in detail, is the energy an object has because of its state of motion. It is also called the object's translational kinetic energy if it is moving in a straight line. Kinetic energy formula is half mv squared, and it can be shown in general that the work done by an object is equals to the change in kinetic energy. Now let's look at an example. The extinction of dinosaurs and the majority of species on Earth in the Cretaceous period, which is 65 million years ago, is thought to have been caused by an asteroid hitting the Earth near the Yucatan Peninsula. The resulting ejecta caused widespread global climate change. If the mass of the asteroid was 10 to the power 16 kilograms, diameter in the range of about 4 to 7 miles, and had a speed of 30 kilometers per second, what was the asteroid's kinetic energy? They want us to find the kinetic energy of the asteroid. And we know the kinetic energy is given by 1/2 mv squared, where m is the mass and v is the velocity of whatever object you're looking at. And in this case, they give us the mass of an object as 10 to the power 16 kilograms, and they give us the velocity of the meteoroid as 30 kilometers per second. So see, they give us kilometers here. Now we need to convert it into SI units, so that basically means is I have to multiply 1 kilometer equals 1,000 meters. So now I have to multiply these two numbers together to get 30,000 meters per second, right? Because the kilometer is going to get canceled. Okay, now all we have to do is, since we have our mass and we have our velocities, we need to be able to plug those into these two numbers. So that basically means is I have to do 1/2 10 to the power 16 kilograms and 30,000 meters per second. And when I do the calculation, my final result for my kinetic energy comes out to be 4.5 times 10 to the 24 joules. Well, that's well and great. We have a number that comes out, but we have to be able to figure out what it actually means, this number joules. So now let's convert it to megatons of, say, TNT. How much force did that asteroid hit with? So in general, we know that 1 megaton of TNT is equals to 4.184 times 10 to the 15 joules. Now, in order to convert this joules into TNT, what do we have to do? We have to multiply our answer with 4.185 times 10 to the 15 joules when 1 megatons of TNT. Okay? So go ahead, put it into your calculator and calculate for megatons of energy. My answer comes out to be approximately 10 to the power 9 megatons of TNT, which is a really, really large number when you think about it.